Welcome to this coding problem walkthrough. Today, we'll be solving problem number 1830, titled Minimum Number of Operations to Make String Sorted. In this problem, we'll explore how to determine the minimum operations needed to sort a string, leveraging algorithms and key concepts in combinatorics and optimization. Let's dive in and break it down step by step. The problem we're tackling is to determine the minimum number of operations required to make a given string sorted in lexicographical order. The string, denoted by S, consists of lowercase English letters and is one-indexed. To solve this, we are allowed one type of operation, picking any character from the string and inserting it at the very beginning. The goal is to achieve the sorted version of the string with the fewest such operations. However, because the result can become very large, we must return the answer modulo 10 to the power of 9 plus 7. For the input, S is guaranteed to be a string containing lowercase letters and has a length between 1 and 30,000. The output is simply an integer representing the minimum number of required operations, modulo 10 to the power of 9 plus 7. To understand this better, let's dive into some examples. Consider the first example where the input string is CBA. To make it sorted in lexicographical order, we need a total of 5 operations. First, we pick A and move it to the beginning, forming the string ACB. Next, we pick B and place it at the beginning, resulting in BAC. Then, we pick B again and move it to the start, giving ABC. Afterward, we pick C and place it at the beginning, forming CAB. Finally, we pick C again and move it to the beginning, resulting in the sorted string ABC. Therefore, the minimum number of operations is 5, which we return as the output. Continuing with the second example, if the input is ABA, the process requires 4 operations, and the output is 4 modulo 10 to the power of 9 plus 7. In the case of ABA, the operations to sort it are as follows. First, we take the second B and place it at the beginning, producing BA. Then, we take the first B and move it to the beginning, forming ABA. Next, we pick the last and insert it at the start, resulting in ABA. Finally, we take the second to last and move it to the beginning, giving us the sorted string AOB. This requires a total of 4 operations, so the output is 4. Now let's look at a simpler example. If the input is ABCD, the string is already sorted, so no operations are required. The output in this case is 0, as the string is already in lexicographical order. There are several constraints and edge cases we need to consider when solving this problem. First, the length of the string, S, is between 1 and 30,000 characters. Additionally, the string only contains lowercase English letters, meaning characters range from A to Z. The result must always be returned modulo 10 to the power of 9 plus 7. For edge cases, if S is a single character string, like A, no operations are needed since it is trivially sorted, and the output is 0. Similarly, already sorted strings like ABC or AIC require no operations, so the output is also 0. On the other hand, reverse sorted strings like ZYX require the maximum number of operations to sort. Finally, strings with repeated characters, such as AAA or AB, must be handled correctly, ensuring duplicates are accounted for in the computation of operations. To solve the problem of finding the minimum number of operations to make the string sorted, we considered different approaches. The first is the brute force method, where we simulate all permutations of the string. By generating all possible permutations, sorting them, and identifying the position of the original string in the sorted sequence, we can compute the number of operations required. However, this approach involves generating permutations, which has a factorial time complexity of O(n). For strings of even moderate length, say n greater than 10, this becomes computationally infeasible, making it impractical for larger inputs. On the other hand, an optimized approach leverages the factorial number system combined with a Fenwick tree. Here, the problem is reframed as calculating the rank of the string in the sorted order of its permutations. Using pre-computed factorials, we can quickly calculate the contributions of prefixes in the ranking process. Additionally, the Fenwick tree helps us efficiently track and query character frequencies. This allows us to count how many smaller characters are available at each step, making the process both efficient and scalable. Now, to break down the optimized approach further, there are key observations that make this strategy effective. The rank of a string lexicographically is determined by counting how many permutations start with characters smaller than the current character at each position. Factorials are crucial for calculating the number of permutations for these smaller prefixes, while the Fenwick tree efficiently handles frequency management of the characters. This ensures that for every character, we can quickly determine its contribution to the rank. As for the complexity, pre-computing factorials takes O, n, and each Fenwick tree operation, whether it's an update or a query, takes O, log n. Since we iterate through each character of the string, the overall complexity is O, n log n. This approach is not only efficient but also avoids the need to explicitly generate permutations, which is a significant advantage. We also considered an alternative approach based on counting inversions in the string. By identifying pairs of indices where characters are out of order, the number of operations needed to sort the string can be estimated. A merge sort-based algorithm can compute this in O, n log n. However, this method doesn't provide a direct way to calculate the rank of the string, which limits its alignment with the problem requirements. The chosen strategy for this problem is the optimized approach using the factorial number system and Fenwick tree. It provides an efficient solution that directly addresses the problem's requirements. The key insight here is that the factorial number system allows us to compute the rank of the string precisely, while the Fenwick tree dynamically tracks and queries the frequency of characters as we process each one. This combination ensures an O, n log n, solution, avoiding the exponential complexity of brute force and the limitations of inversion counting. When considering trade-offs, brute force is conceptually straightforward but computationally prohibitive due to its factorial time complexity. The factorial number system with the Fenwick tree, while requiring a deeper understanding of advanced data structures, offers the best balance of efficiency and scalability. Counting inversions, though efficient, is less intuitive and lacks the direct computation of lexicographical rank needed for this problem. Ultimately, our chosen strategy aligns perfectly with the problem's demands, making it the most optimal and practical solution. The problem minimum number of operations to make strings sorted revolves around transforming a given string into its lexicographically sorted form using the minimum number of allowed operations. The operation involves selecting any character from the string and moving it to the end. To tackle this efficiently, the solution leverages combinatorics, modular arithmetic, and Fenwick trees. First, we pre-compute factorials and their modular inverses. Since permutations and combinations calculations are fundamental to the solution and are repeated multiple times, pre-computing these values modulo 10 to the power of 9 plus 7 ensures efficiency. Modular inverses are calculated using Fermat's little theorem, which simplifies division under modulo. Additionally, we initialize a Fenwick tree to dynamically track character frequencies. This data structure allows us to determine how many characters are smaller than the current one in logarithmic time, which is a key step in the algorithm. Next, we iterate through the string one character at a time. For each character, we determine how many characters smaller than the current one are still available using the Fenwick tree. This helps us calculate how many valid permutations can be formed if we place the current character at its position. After processing a character, we update the Fenwick tree to reflect that the character has been used by decreasing its count. Simultaneously, we maintain a running total of the permutations computed at each step. These permutations represent the number of operations required to move the current character to its correct position in the sorted string. Throughout these calculations, modular arithmetic ensures that the result remains within bounds. At the end of the iteration, the accumulated total gives us the minimum number of operations needed to sort the string. Several key insights drive the efficiency of this algorithm. First, by pre-computing factorials and their modular inverses, we handle the combinatorial calculations for permutations quickly. Modular arithmetic is essential for managing large numbers, as the results of these calculations can grow exponentially. The Fenwick tree plays a crucial role in dynamically tracking the frequency of characters, enabling us to perform efficient queries on how many smaller characters are available at each step. Together, these elements allow the algorithm to run in O, n log n, time. The space complexity is O, n plus 26, with n accounting for factorials and modular inverses and 26 for the character frequencies, corresponding to the lowercase English alphabet. This combination of efficient data structures and mathematical tools ensures the algorithm is both scalable and performant. Finally, edge cases highlight the robustness of the algorithm. For a single character string, no operations are needed, as the string is already sorted. Similarly, for a string that is already in lexicographical order, the algorithm correctly identifies 0 operations. On the other hand, a reverse-sorted string represents the worst-case scenario, requiring the maximum number of operations. The algorithm handles this by iteratively counting the permutations needed to move each character to its proper position. This approach not only guarantees correctness but also maintains clarity and efficiency, making it well-suited for a variety of input scenarios. By balancing these considerations, the solution effectively addresses the problem's constraints while remaining computationally efficient. To solve the problem of finding the minimum number of operations to make a string sorted, we start by importing the factorial function from the math module. We then define our solution class and the method makeStringSorted, which takes the input string s. Inside the function, we first set up a constant mod, which is 10 to the power of 9 plus 7, to ensure our calculations remain within the bounds of modular arithmetic. Next, we determine the length of the string s and pre-compute the factorials up to n. This helps us calculate combinations efficiently later in the code. Using a loop, we iteratively compute the factorial for each number from 2 to n, storing the results in the fact array and taking results modulo mod at each step. Additionally, we compute modular inverses of these factorials using Fermat's little theorem. By initializing the inverse of the factorial of n and iterating downward, we calculate the inverse factorial for each number, storing it in the inv_fact array. The comb function is then defined to calculate combinations efficiently using the pre-computed factorial and inverse factorial arrays. After this setup, we count the frequency of each character in the string s using an array frequency, where each index corresponds to a letter from A to Z. Finally, we initialize a variable result to 0, which will hold our final answer as we iterate through the string. Now, we iterate through each character in the string s using a loop. For each character, we calculate its index in the frequency array based on its ASCII value. We then look at all characters smaller than the current character. For each smaller character, if its frequency is greater than 0, we temporarily reduce its frequency by 1 to calculate permutations where the smaller character is fixed. The number of permutations is determined using the factorial of the remaining characters, and we adjust this count by dividing out the factorial of repeated characters using the pre-computed inverse factorials. This ensures we account for duplicate arrangements in the permutations. The calculated permutation count is added to the result, and we take the modulo to keep the result within bounds. After processing the smaller characters, we restore the frequency of the smaller character to its original value and proceed with the current character by reducing its frequency in the array. After completing the loop for all characters, the final result, which represents the minimum number of operations, is returned. Here, we begin by importing the necessary Java utilities and defining our solution class. Inside this class, we declare a constant mod to handle large numbers while ensuring results fit within the constraints of modular arithmetic. The main function, makeStringSorted, takes a string s and calculates the minimum number of operations required to make it lexicographically sorted. We first determine the length of the string and initialize 2 arrays, fact for storing factorials and inv_fact for their modular inverses. The fact array is pre-computed using a loop, where each factorial is calculated modulo mod. Similarly, the inv_fact array is populated by first computing the modular inverse of the largest factorial using the helper function modInverse, and then working backward to compute the rest. Finally, we initialize a frequency array frequency to count the occurrences of each character in the string, helping us track how many times each character appears as we process the string. We now calculate the result by iterating through each character in the string. For each character at position I, we convert it to its corresponding index in the frequency array using charIndex. We then check all characters smaller than the current one to determine the number of permutations that can be formed if one of these smaller characters is fixed at position I. If a smaller character has a non-zero frequency, we temporarily decrement its count in the frequency array, calculate the number of permutations using the factorials and modular inverses, and then add this count to the result. The permutations are calculated as the factorial of the remaining length multiplied by the modular inverses of the frequencies of all characters currently in the frequency array. After considering each smaller character, we restore its frequency to maintain the integrity of the array. Finally, we decrement the frequency of the current character, as it has now been processed. This process ensures that we count all valid permutations while respecting the constraints of modular arithmetic. To support the modular arithmetic used earlier, we define two helper functions. The first, mod inverse, calculates the modular inverse of a number x modulo mod using Fermat's little theorem. It does this by calling the second helper function, power, which efficiently computes the result of x raised to the power of y, modulo mod, using an iterative approach known as modular exponentiation. The power function works by repeatedly squaring the base and reducing the exponent by half, checking at each step whether the current exponent is odd to adjust the result accordingly. This method ensures that calculations remain efficient even for large numbers. By integrating these helper functions, we ensure that the modular inverses and powers required for the main logic are computed accurately and efficiently, enabling the solution to handle the constraints of the problem seamlessly. The problem we're solving is to find the minimum number of operations required to transform a string into its lexicographically sorted order. The operation involves selecting any character from the string and moving it to the end, with each operation counting as one step. To ensure our result fits within computational limits, we computed modulo 10 to the power of 9 plus 7. Let's start with an example, the string CBA. First, we pre-compute factorials up to the length of the string, which is 3 here. The factorial values are 1, 1, 2, 6, representing 0, 1, 2, and 3. We also compute modular inverses of these factorials using modular exponentiation to facilitate division under modulo arithmetic. These inverses are 1, 1, 500, 0, 0, 0, 0, 0, 4, 1, 6, 6, 6, 6, 6, 6, 6, 8. Lastly, we initialize a frequency array to track the number of occurrences of each character, which here results in 1, 1, 1, 0, 0, since a, b, and c each appear once. These precomputations will help us efficiently calculate permutations as we process the string. Now, we process each character of the string, starting with an initial result of 0. For the first character, c, we calculate the number of permutations for characters smaller than c, which are a and b. For a, we temporarily decrease its frequency by 1 and calculate the permutations. Using our pre-computed values, the total number of permutations is 2, which we add to the result, making it 2. After restoring the frequency of a, we perform the same calculation for b, adding another 2 permutations to the result, which now becomes 4. After processing c, we decrease its frequency by 1. Next, we move to the second character, b. Here, we calculate permutations for the only smaller character, a, which adds 1 to the result, making it 5. We then decrease the frequency of b by 1. Finally, for the last character, a, no smaller characters remain, so no permutations are added. At this point, all characters are processed. After processing the last character, its frequency is decreased by 1. The final result for this example is 5. Moving to a second example, let's consider the string BAC. We follow the same setup, pre-computing the factorials 1, 1, 2, 6, and their modular inverses 1, 1, 500, 0, 0, 0, 0, 0, 4, 1, 6, 6, 6, 6, 6, 6, 6, 8, and initializing the frequency array as 1, 1, 1, 0, 0. For the first character, b, we calculate permutations for the smaller character a. This adds 2 to the result, making it 2. We then decrease the frequency of b by 1. For the second character, a, no smaller characters remain, so no permutations are added. After processing a, we decrease its frequency by 1. Finally, for the last character, c, no smaller characters remain either. The frequency of c is decreased by 1, and the final result for this example is 2. For the third example, consider the string ABCD. Since this string is already in lexicographical order, no operations are required, and the result is 0. This example highlights an important observation: if the string is sorted initially, the result is directly 0. To summarize, the key insights of this problem include the pre-computation of factorials to avoid repetitive calculations, the use of a frequency array to efficiently track character availability, and the iterative process of counting permutations for smaller characters at each step. Modular arithmetic ensures that all calculations stay within bounds, making the algorithm highly efficient. By combining these techniques, we can solve the problem optimally for any given string. Here, we begin by analyzing the time complexity of the solution, which can be broken into distinct components. First, we have the pre-computations for factorials and modular inverses. Pre-computing factorials involves iterating from 2 to n, which results in n time. Similarly, pre-computing modular inverses requires iterating from n down to 1, and this also takes n time. Together, these pre-computations contribute n to the overall complexity. Next, we calculate the frequency count of each character in the string. Since this is done in a single pass through the string, and the string has a length of n, the frequency counting step also takes n time. These two components form the foundation of our analysis so far. Now, let's look at the main iteration, where we process each character in the string. The outer loop runs once for each character, meaning it has a time complexity of n. Within this loop, we iterate over all possible smaller characters, which is at most 26 iterations, as there are only 26 lowercase English letters. This constant iteration makes the inner loop 1 per character. Inside the inner loop, we calculate the number of permutations for the remaining characters. This involves iterating over the frequency array, which is of size 26 and also constant, so this step is 1. Combining these, the total work within the nested loops is 1 per outer loop iteration. Since the outer loop runs n times, the total contribution here is n. Additionally, modular arithmetic operations, such as modular exponentiation and multiplication, are constant time 1. Their effect is included within the loops, so they don't add extra complexity. Bringing everything together, the total time complexity of the solution is n. Next, we analyze the space complexity of the solution. The first major component comes from the factorial and modular inverse arrays, which each have a size of n plus 1. These arrays contribute n to the space complexity. Then, we have the frequency array used to store the counts of each character. This array has a fixed size of 26, regardless of the input string length, so it contributes 1 space. Lastly, we have a few integer variables, such as the result variable and indices, which also use constant space 1. When we combine these components, the total space complexity of the solution is n, as the factorial arrays dominate the overall usage. Let's now compare this optimized approach to a naive or brute force solution. In the naive method, we would generate all permutations of the string, sort them, and count how many permutations are lexicographically smaller than the given string. Generating all permutations has a time complexity of n, and then sorting these permutations would add another n. *n, making it computationally intractable for larger strings. By contrast, the optimized solution avoids generating permutations entirely and instead calculates the count using combinatorics and modular arithmetic. This reduces the time complexity to n, which is a significant improvement. Furthermore, the time complexity remains n across best, average, and worst cases, as the algorithm performs the same operations regardless of the input. Similarly, the space complexity is consistently n, dominated by the factorial arrays. This makes the current solution both efficient and scalable. Finally, let's solidify our understanding with a mathematical proof for the big O complexity. The pre-computations involve linear iterations for factorials and modular inverses, contributing n. The nested loop that processes each character in the string involves constant time operations for each character, leading to n overall. Modular arithmetic operations, such as modular exponentiation and multiplication, are 1 and only occur within the loops, so they do not increase the complexity further. When we combine these elements, the total time complexity remains n. For space complexity, the dominant factor is the factorial arrays, which grow linearly with n, resulting in n space usage. This confirms that both time and space complexities are optimal for this problem. Let's start by discussing some common mistakes that can occur when solving this problem. One frequent issue is misunderstanding the problem statement. Many assume that we need to explicitly sort the entire string, but that's not the case. The goal is to determine the number of operations needed to convert the string into its sorted order, not to actually perform the sorting. Another pitfall involves inefficient factorial computations. Factorials grow very quickly, so computing them repeatedly during the solution can result in significant overhead. Instead, pre-computation combined with modular arithmetic is crucial for improving efficiency. Lastly, many people overlook the impact of duplicate characters. Treating all characters as unique can lead to overcounting permutations. When duplicates exist, you need to divide by the factorials of the duplicate counts to ensure you're not counting the same permutation multiple times. Understanding these mistakes will help you avoid common pitfalls and improve your solution's correctness and efficiency. Now, let's look at a few more challenges that might arise. Incorrect modular arithmetic is another common source of errors. When dividing under a modulus, it's essential to use the modular multiplicative inverse instead of attempting direct division, as direct division isn't valid in modular arithmetic. Neglecting this can lead to incorrect results. Another key mistake is overlooking edge cases. For example, small strings like A or AA, strings that are already sorted, or strings with all identical characters might seem trivial, but failing to handle them properly can cause runtime errors or incorrect outputs. Testing edge cases thoroughly ensures your solution is robust and can handle all input scenarios effectively. From an interview perspective, this problem offers valuable learning opportunities. It heavily involves permutations and modular arithmetic, which are commonly tested concepts. A key insight is understanding how to calculate permutations efficiently, especially when accounting for duplicates. A good optimization pattern is to use Fenwick trees or segment trees to calculate the rank of the current character more efficiently than with a brute force approach. When discussing your solution, it's also important to clearly articulate your thought process, particularly when deriving the formula for counting permutations with duplicate characters. This demonstrates your understanding of the problem. Be mindful of trade-offs as well. While a Fenwick tree-based solution is highly efficient, it can be more time-consuming to implement. In some cases, a simpler approach using pre-computed factorials may be a better choice, especially in time-constrained interviews. Additionally, related problems like LeetCode number 60, permutation sequence, or number 31, next permutation, can provide further practice with similar concepts, so exploring them can be beneficial for strengthening your skills. Finally, let's discuss some alternative approaches to solving this problem. One approach is brute force, where you generate all permutations of the string and count how many are lexicographically smaller. While this method is conceptually simple, it's highly inefficient with a time complexity of O(n), making it impractical for larger inputs. A more efficient alternative is to use Fenwick trees or segment trees. These data structures allow you to maintain frequency counts of characters, enabling you to calculate the rank of the current character efficiently. This approach significantly reduces the time complexity to roughly O(n) log n, but it does come with added implementation complexity. For a balance between simplicity and efficiency, pre-computation with factorials is another viable option. By pre-computing factorials and their modular inverses, you can calculate permutations efficiently. This method is easier to implement but may be less efficient for extremely large inputs due to the O(n) overhead of factorial computations. Each of these approaches has its own trade-offs, so the best choice depends on the specific constraints and requirements of the problem you're solving. Great job making it to the end. To summarize, we tackled problem number 1830 by using combinatorics to determine the number of operations needed to sort a string. This required understanding permutations, modular arithmetic, and optimization techniques. Remember these key takeaways as you approach similar problems in the future. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!